Hey, Year 12s, thanks for coming. It's Friday. It's Friday. Right, guys. So today's lesson, we're continuing the Ionic theme. This is actually going to be the last lesson for Ionic. And then I'm going to do your assessed homework on Ionic. It's only really short. I've just literally grabbed a couple of Ionic questions from some past papers. You'll do it as a homework, and then you'll submit it on the classroom, and I'll mark it. But like I said, this is going to close off Ionics at this stage, and then we're going to move on. And I'm going to move on to metallic. I'm going to do metallic first. I'm actually doing it out of order of the specification because metallic is very standalone. I'm going to box that off, do it nice and quick, throw that away. Then I'm going to do giant covalent, and then switch to the last one, the hardest one of single covalent. But as I said, we're going to box off Ionic today. Well, let's crack on. Should be a nice short lesson today, hopefully. We will see. All right, okie dokie. So I've suddenly realized I haven't got the, before I just do that, I'm just going to view it on YouTube. The reason being is it means that I can pop the chat window out in case you guys want to contribute. There we go. Pop out chat. And then I'll close that one down to save me the bandwidth. Cool, up and running. Let's move on. Right, so Ionic equations. So today's lesson, we've got all three learning types today, which is quite nice. And I love the fact that they're in that particular order. They're actually in the order that is usually the opposite. Yeah, we've got you, understand, able to, and then knowledge. So the first one is understand Ionic equations and when to use them. That's important, that one. The when to use them is going to be really handy. But to understand what an Ionic equation is showing. We'll pick up a load of other little extra words like spectator ion, some of these like, I've got somebody sending me a message. I'm just always wondering whether or not, if someone sends me a message, sometimes there's issues with YouTube. So can you guys just do me a favor? Can everybody say hi on the chat for me? Just to make sure that it's all running. Okay. Cool. Aisha has some questions on the Ionic bonding homework. Okay, so Aisha, would you like me to do the Ionic bonding homework before I do the Ionic equations? I can do that. We can insert this. So insert, print out. I gave you an Ionic homework, which I think, documents, year 12, bonding, Ionic. I think, did I give you ions and melting points? Was it this one? I can ask the questions later. Okay, can. Was it this one? So quite a long homework, actually. What I'll do is I might come back to that if I've got time at the end. Okay, let's quickly run through the homework. Don't think it'll take a huge amount of time. So type of bonding, sodium sulfide. Cool. Let's do the homework first. I think that's our value. Let's do that. So Ionic. If it asked for the crystal type, it would be an Ionic crystal. Yeah. So explanation. So predict the type of bonding and explain the high melting point. Right. Susan Boyle sings Nelly the Elephant. Structure. So bullet point number 1. Na2S is a giant Ionic lattice. Ionic lattice. The bonds, there are electrostatic attractions. I'm just going to put electrostatic attractions, and they put me in a context. So I have to now include those ions, otherwise I'm going to lose that 1 mark. There are electrostatic attractions between, this is the difference between A-level and GCSE. You've got to now use the ions Na plus and S2 minus. Right, strength. Yeah, these bonds are very strong. These attractions, I prefer that. It's not real bonds. These attractions are very strong. And plus 1 plus and 2 minus. Wow, super strong. Yeah, there are millions of these. There are millions of these attractions. Millions of these attractions. These attractions. Lots of energy needed to break all attractions. Lots of energy needed to break all attractions. I like it. Next, sodium reacts with chlorine. Name the type of bonding in sodium chloride. It's ionic. Explain why the melting point of sodium chloride is so high. Same process, so it's very repetitive. You're seeing the questions from papers, guys. Susan Boyle sings None of the Elephant. We do the same process. Structure, it's a giant ionic lattice. The electrostatic attraction between, so this is the elec-stat between, and we've put me in a context, Na plus and Cl minus. Strength, very strong attractions. Millions of them. I'm obviously, you can't do this in your exam the way I'm doing here. Lots of energy. I'm just shortcutting it because I did the first one properly. That is as I would do that in an exam. Just to point out, by the way, I wouldn't leave the S's and the B's in. I'd just do that. Yeah, I'd just have it as bullet points like that. Sometimes I like to write these in the margin. Help me remind me. And then they ignore anything in the margins, by the way, just so you know. Next. Suggest why the melting point of sodium iodide is lower than that of sodium bromide. Right, so sodium ion's the same, 1 mark. The iodide ion is much larger, larger than Br minus ion. Yeah, so weaker electrostatic attraction. So weaker elec-stat attract. Yeah, I like it. You could have gone the other way around. You could have said that Br is smaller, so therefore has a stronger electrostatic attraction. You could do that way around if you like. But it's interesting. It's only 1 mark because, of course, the sodium's the same. It's quite clever, that. Like that one. Magnesium oxide has a melting point of predict the crystal type. It's an ionic crystal. There we need. It's nice to see the crystal word there, crystal type. Suggest why its melting point is so high. Susan Boyle sings Nelly the Elephant. We've got no choice. You just Susan Boyle sings Nelly the Elephant. I'm going to do those in that space. I've got less space there. So what I'm actually going to do is I'm just going to run them into each other. S, right, comma, yeah, right, comma, right, comma, right. I'll just string them all together. Yeah. So it's a giant ionic lattice held together by the strong electrostatic attraction between Mg2 plus and O2 minus. There are millions of these attractions. Millions of these attractions. Oh, the attractions are very, very strong. Loads of energy needed to break. I changed the order there because I was rushing it. Shouldn't have. Thallium bromide is a crystalline solid with a melting point of 4. It's still pretty high. Suggests the type of bonding present. Right. So guys, I don't know what thallium is. Where the hell's thallium? Yeah, this is a great example of where you have to use your GCSE rules. Love it. Let's use it. A-level. Where the heck's thallium? Where is thallium? It is a metal. So we know that the line's there. It's clearly in the metal side. Probably going to be ionic. Yeah, so this is ionic. Do you see the repetitive nature of these questions? And then run Susan Boyle sings Nelly the Elephant. Done. Write an equation for the formation of thallium bromide from its elements. Where's thallium? What was thallium? Did they give me the symbol? It did. TL. TL solid plus Br2 liquid goes to TLBr balance. We're done. Boom. And that's what that is, a solid as well. There we go. State symbol's not required, of course, but it's nice to do so. Yeah, nice reminder. Bromine's a liquid. Please remember this. Love that. The bonding in ammonium chloride is oh dear. Guys, I'm really sorry. That's really tricky, that. Because the answer is D. So all of them. The bonding in solid ammonium chloride it's everything. The reason being is, just to show you why, is because ammonium chloride is NH4Cl. Now, overall, this is really clever. If they said in that question, which one of these explains why ammonium chloride has a high melting point, you'd go ionic. Yeah, the high melting point is because it's ionic. However, in reality, if you look at the bonding, you've got the ammonium ion, and this is something that you haven't seen yet. You're going to, though, that one there. That there is called a dative covalent bond. Yeah, and we'll be coming to that later when we do simple covalent, or just covalent, and then Cl minus. So we've got an ionic bond, an ionic attraction there. We've got standard covalence here, but then also a dative covalent there. So it's actually all three. What a nightmare that is. Sorry, guys, that's beyond you. My bad. Draw the dot and cross diagram for strontium chloride. Okay. So strontium is a 2+. Periodic table, strontium is a 2+. We need 2 chloride ions. Right. So SR, show outer shells only. What that means is SR doesn't need it at all because SR's lost its outer shell. Winner. Right, now add your chloride ions. Outer shell only. Yeah, circle, 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 circle. So strontiums were crosses. There we go. And then we need another one because it's a 2+. Circle, 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 cross. I've changed my routine there. Shouldn't do that. There we go. 2 marks. Done. Winner. You do need 2 of them, though. Tricky that. Most people forget to do 2. Next, a solution of strontium nitrate was prepared with strontium oxide and write an equation, including state symbols. Strontium nitrate, SR brackets NO3 twice, aqueous is the solution. Was prepared, from strontium oxide, which will have been a solid. Strontium's a 2+, so that's just that. Plus nitric acid, no U acids, HNO3, aqueous. Goes to SR brackets NO3 close brackets 2. Aqueous. All salts, all nitrates are going to be aqueous. Plus water. Balance the equation. I'm done. Adds up. Liquid. Oof, easy to lose that one. Done. I like it. Clever game. Next, element R is in group 1 in the periodic table. T is in group 6. R, T are not the symbols for the elements. The compound will have the formula. That's quite clever, that. So R is group 1, so that's going to be R1+. T is group 6, that's going to be T2-. Crossing down, it's going to be R2T. So it's D. Compound R and T will be bonding predominantly as ionic. In terms of electrical conductivity, the compound RT will conduct when solid? No. Conduct when solid? No. Conduct when liquid? Yes. But not when solid? Yes. Not conduct solid? No. So the answer is C. Clever game. Like it. Properties. Chlorine has formed a compound with magnesium and with carbon. Draw the dot and cross diagram for magnesium chloride. Only the outer shell. Mg loses its outer shell. Love metals for that. Chlorine, it's the same one, just with magnesium instead of strontium. Nice, you see the repetitive nature of exams. This is why we do them. It's why we practice, because we know this is the routine. I went back to doing my normal routine there, and it's nice to put the X close to the magnesium, not that it really matters. There we go. Include the charges present. Suggest why the melting temperature of magnesium oxide is higher than that of magnesium chloride, even though they are both 100%, almost 100% ionic. Right, hang on a minute. Magnesium oxide, MgO, versus MgCl2. Right, so this one, so bullet point number 1, magnesium oxide contains, so I'm going to write bullet point number 1. Yeah, bullet point number 1. MgO contains Mg2+ and O2- ions. Next bullet point. MgCl2 contains Mg2+ and Cl1- ions. Right, 1 mark, 1 mark. Right, the magnesium has remained the same, so we're going to ignore it. Next, third bullet point. O2- is, well, is it going to be bigger or smaller? Ooh, it'd be nice to mention size here as well. So anyway, before I do that, let's do bigger difference in charge. Bigger, I feel like I'm going to run out of space. Bigger difference in charge between Mg2+ and O2-. I like it, 1 mark. Yeah, it's also nice to mention the size, just as a kicker. If you look at the periodic table, oxygen now has the configuration of neon, 2 shells. It's bigger though, but chlorine has 3 shells and is now the configuration of argon. Chloride's massive. Yeah, also, O2- is smaller than Cl-. So stronger, elec, stat, attract. Stronger, elec, stat, attract. I'm done. Okay, the lattice composed of this is stronger than the lattice composed of that. Okay, explain in terms of charges, of the charges on the ions and the size of the cation. Oh, isn't that interesting? That's weird. So the question is being very specific. Explain in terms of charges on the ions and the size of the cations, specifically focused on the cations, why this is so. Okay, two bullet points. So difference in charge between Mg2 plus and O2 minus is larger than Mg1 plus and O1 minus. Stronger attract, stronger elect-stat attract. Next bullet point, size of the cation. Oh, that's weird. So hang on, cations are positive. So, okay, who's going to be bigger? So, actually, I'll just do it here. So what we know is that we've got magnesium atom, 2 electrons in its outer shell, 3 shells in total. Right, we're going to remove the first one. It's going to shrink and become Mg1 plus. It's now got 1 electron in its outer shell. But then if we take another one away, there's the Mg1 plus. We're going to remove another. Blimey, it's going to become and it's lost an entire shell. Yeah, that there still has 3 shells and is plus 1. 3 shells plus 1. This is now 2 shells plus 2. That's way smaller. Way smaller. Holy mackerel. So then we're just going to state, nice and easy, Mg2 plus is smaller. Smaller than Mg1 plus. Next, which of the following ions has the smallest ionic radius? Ooh, right, that's tricky. Periodic table. Right, so my choices, this is harder. This one requires me to have the table in front of me, really. Right, calcium, potassium, sulfide, and chloride. Okay, oh, hang on a sec. So smallest, immediately, I'm going to say no and no. We remember the nota bene here, nota bene, negative ions are massive. Yeah, they're massive because they've gained an extra electron. Gain electron, so more electrostatic repulsion within the shell. So more electron repulsion. So they get massive. So immediately, if we're looking for the smallest, those two, hells no. But now we need to look at these ones. Calcium 2 plus and potassium plus. Let's have a look. Right, calcium and potassium. Okay. So they have the same shielding. They're both becoming argon. Yeah, both of them. K plus and Ca2 plus are both argon configurations. So now what we need to do is look at that configuration. So if we look at the argon configuration, so we have K plus being 2,8,8. This is the GCSE one. Yeah, and that's plus 1. Whereas Ca2, it's nice to use the GCSE every now and again. 2,8, 2 plus. So we know that this one's going to be smaller. It's highly more charged. More charged, the smaller they become. But it's also nice to realize that in terms, if we wanted to explain this, potassium has 19 protons versus calcium, who have 20 protons. Same electron configuration, but more protons and increased plus 2 charge. Yeah, calcium is definitely going to be the smallest. So the answer is A. Clever game, though. Next, which of the following results from the most polarized cation? In the most polarizing cation. So we know, we talked about polarization and this idea of distortion and electron maps. We talked about the idea, if you have a positive ion and then you put a negative ion nearby it, the negative ion will become distorted. Yeah, so what it actually looks like is this. Yeah, it becomes distorted. Yeah, real. There's no such thing as perfect spheres. They just don't exist. Yeah, but if you want to polarize it more, what you want to have is smaller. If you're smaller, then you will have a much more polarizing effect, much bigger polarizing effect. Yeah, like that, there we go. But also you want to amp up the charge as well. If you could do that as a 2 plus, holy moly. Yeah, it's probably going to become covalent at that point. Yeah, so we want small and highly charged. Radius small, so it's either, so that you don't want them to be large. And then the charge, we want it to be large. The answer is B. I like it. Which of the following ion has the smallest smallest radius? So we're saying smallest ion again. So I can get rid of those that neither D or A because they're negative. Yeah, negatives are going to be massive. It's also nice to look at the fluoride option, to be fair. It's quite interesting, that one. Because, in fact, they've done something really clever. Oh, look what they've chosen. Oh, love that question. Are they all isoelectronic? Yeah, do you remember the words isoelectronic? That means they have the same electron configuration. The word iso means same in chemistry. Isotope, same identity. Yeah, isomer, same parts. Yeah, it's cool, that. So iso, same electronic configuration. So fluorine had 9 electrons originally. It's now got 10. So fluoride becomes 1s2, 2s2, 2p6, all in a square bracket, -1. It's gained 1. Magnesium 2+. Magnesium 2+ loses it and becomes neon, the same as fluoride does. 1s2, 2s2, 2p6, 2+. That's hilarious. And then sodium's got the same 1s2, 2s2, 2p6, lost 1 electron because it had the 3s1. And then the oxide's the same. Isn't that cool? They're all isoelectronic. Lol, 2-. The biggest one is going to be O. That's going to be the largest ionic radius. Yeah, and the smallest is going to be magnesium. Smallest, love it. And they asked for the smallest, so go for that. I love that question. Really clever. Yeah. Potassium combines with iodine to form potassium iodide. Which of the following describes the bonding in it? So potassium metal is metallic, so that one is correct there and there. Iodine is covalent, so there and there. Oh, lol. There we go. The only one. It's the only one with all 3 ticked off being correct. Isn't that clever? I like that game. Nice. D. Potassium iodide, by the way. Potassium iodide is going to be like, covalent character. It's going to have some quite heavy distortion. Oh no, less distortion than lithium iodide. Potassium's larger. Not as bad as I thought. Right. Each of these diagrams shows the trend in ionic radius for the 4 sequence of ions in the diagram. What? Each diagram shows the trend in the ionic radius for 4 sequences of ions. Ionic radius, ion. Oh my goodness. Okay. Oh, I see what they're doing. That's clever. Which diagram represents this sequence? Lithium, sodium, potassium, rubidium. Right, table. We know that the atoms, let's do atoms in red. The atoms look like this. They're getting larger. Yeah. Let's now do the ions. Let's now do the ions in green. They're doing exactly the same trend, but they're smaller because they're positive. Yeah? Isn't that clever? So it's increasing inside in a fairly uniform way as well. So there's only one where the ions are increasing. A. That's clever. They're increasing in size. Ionic radius is growing, and we're going down the group. Fine. Next. Which diagram shows the trend in ion radius for this sequence? Sodium, magnesium, aluminum, silicon. We're going across the group now. So that's tricky. Right. So we now need to go atoms, sodium, magnesium, aluminium. We know that they get smaller as we move across the period. But now we need to do the ions. Oh dear, guys. So sodium's atom. I can't zoom in. Sodium's atom, sodium's ion. I should do it in a different color. Yeah, sodium's ion. It loses an electron. Yeah, it loses an electron, becoming an A+. Magnesium does the same thing, but it loses 2. Had a smaller atom to begin with, but then it will lose 2 electrons and become a much smaller ion. That's Mg2+. Aluminium does exactly the same thing. It was a smaller atom because it had more protons, but similar shielding. And then it's now got a +3 charge. Holy moly. So it now becomes that. Now silicon's a tricky one because silicons can become a +4 or a -4. In reality, it doesn't really do any of it. So I don't really know. So the answer is they get smaller. What ion have they given me in the question? Silicon 4+. So they're going to become way, way smaller. Way smaller. D. So there's D. Next. Lattice energies. So lattice energies is the equivalent of melting points. Look at it like that. I've done this one with you guys already, actually. Yeah. So in this case, Cl minus versus F minus. Yeah, Cl minus, F minus, same charge, but F minus is smaller than Cl minus. Stronger electrostatic attraction. Stronger electstat, we're done. Isn't that cool? Electstat. Next, Na plus versus Mg2 plus. We've got to mention charge and size here. Sodium 1 plus, Mg2 plus. So that's more complicated. So Mg2 plus, smaller than Na plus. Mg2 plus, more charged than Na plus. Stronger electstat attract. I'm done. That brings the homework to a close, I believe. I don't know how many the homework was out of. Guys, you can mark it and you can add. Can someone do me a favor and tell me how many marks it's out of? And then I can crack on with today's lesson. I know that I'm now running majorly late. The Ionic equation shouldn't take me a huge amount of time. Oh, I've only got 15 minutes. Lol. I think I can do this then. So you can let me know how many it's worth on the chat. That'd be really handy. You can add yourself to the score sheet. That one there. So this is, I don't know which Ionic homework this was on the classroom. Nope. Classroom. This was just E. This was Ionic homework 2, ions and melting points. Ionic homework 2. Keyboard. Ionic homework 2, ions and MPT. Here we go. I've just made that other one vertical. It's hilarious. I could probably wrap it as well. There we go. Perfect. You can let me know how many it's out of. That'd be grand. Sorry. Let me go. Hang on. Any idea how many it's out of? Work it out. 3, 1, 2, 1, 3, 3, 1, 1, 2, 2, 1, 1, 1, 3, 3, 2, and 1, and then 1, 1, 1, 1, 1, 2, and 2. Add those all together. Holy moly, it's quite a long homework actually, wasn't it? How many people? What do people think it is? Let's get rid of that. This one. Out of 39. Oh, interesting. I'll check. I think. Let's have a look. 3 plus 1 plus 2. So on each page, 6, 8, 5, 6, 6, 3, 2, and 4. That makes it easier. Right now I can just add those all together. So 6 plus 8 plus 5 plus 6 plus 6 plus 3 plus 2 plus 4. It's out of 40. Dead out of 40. Wowzer. It's out of 40. Amazing. Louis, 37. Outstanding. Well done. Great score, that. Great score. Amazing. And I haven't done any more. It's good going through the homework, though. It's way worthwhile doing it. Ionic equations. $10 minutes. We'll see. In chemistry, there are many equation types. Many equation types. Number one, word equations. You'll never write these anymore, guys, at A level. I say that never. Very unlikely at A level. Then we get chemical. Some people like to call that symbol equation. The problem is, in reality, chemical equation. Yeah, in reality, if they ever ask, so that's just called an equation. If they ever say write an equation, yeah, they immediately mean chemical, which you can then, put as symbol. You know what it is. It just means you're gonna have the symbol one. I think at 39. I think it's at 40, but I might be wrong. But anyway, so third one is ionic equation. So in an ionic equation, the difference between ionic and chemical is the fact that a chemical, technically, it gives you what's called the overall reaction. It's kind of everything that's going to be doing stuff. But the problem is that not all stuff does anything. So first question, when to use an ionic equation? Answer. Number one, when they ask. I know that sounds funny. When they ask for it. Yeah, in the question it says, write an ionic equation. Fine. Is there any other scenarios where it doesn't actually get said? No, not really. They usually say in the question, write the ionic equation for this process. And you could argue that you should be write the equation. No, but if they just said write the equation, you have to write a full one. They will always say it. So what is an ionic equation? Question number two. What does an ionic equation show? Answer. Number one. Answer. The species, yes, I'm using that word from biology, we use it in chemistry as well. It's the species can encompass anything that's an atom, an ion, a molecule, it can be anything. Yeah, the species doing the work. I know that sounds weird. Yeah, the species doing the work. Yeah. So what does an ionic equation show? The species doing the work. And number two, I'm changing my color because this is the opposite, not seen. What are called spectator. Do not see spectator ions. So the word spectator, that word simply means onlooker. Yeah, this is a spectator at a concert, a spectator at a sports event. Yeah, they are not playing football, they're simply watching it from a distance. They are not actually doing anything. Let me show you an example of this. So the reaction between hydrochloric acid and sodium hydroxide. We realize that this chemical equation we've been writing down for years. Let's add in some state symbols. Acids are aqueous, the base is aqueous, water is liquid, and the salt is aqueous. This here is called the overall equation. This is just called the equation or the overall equation. Now, here's the thing. In reality, that's not really happening. Because here's what's actually happening. You've got a beaker of HCl. Now, HCl is covalent, but when it goes into water, it ionizes. You've got a beaker of these guys. Yeah? Sodium hydroxide. What does sodium hydroxide look like? Sodium hydroxide went in as an ionic salt, metal, non-metal, and then dissolved, ionized, to form Na+ and OH-. So whenever you have the symbol aqueous, it means it's split into its ions, if ions are available. Yeah, so if I now mix these two together, which is what we've been doing for years, we mix them together, and what do you get? you see, by the way, what I'm going to do is I'm going to show them all in there, and then I'm going to change them. So H plus, Na plus, OH minus, and Cl minus. Here's what now happens. The H plus and OH minus now come together to form water. But the NaCl doesn't do anything. It actually just continues to float around the way it was before. So it will be classed as spectator. So what that means is I can take this overall equation and I can turn it into an ionic. So let's write the whole thing out again. HCl plus NaOH goes to H2O and NaCl. Let's now turn everybody into their ions. H plus Cl minus plus Na plus OH minus goes to H2O plus Na plus and Cl minus. And what you realize is that this Na plus has appeared on both sides of the equation, so it disappears, and the Cl minus will disappear as well. The overall ionic equation is H plus OH minus goes to water. Yeah, this is the ionic equation for neutralization. Red, ionic equation for neutralization. Let's try something else. Neutralization. Let's try something else. And what you realize is, by the way, guys, it's the answer to these questions is in the state symbols. Yeah, if you see aqueous, you can divide it into its ions and then decide whether or not they cancel out or not. Let me show you another one. This is where your chemical tests now appear. Yeah, chemical tests. So I'll do another lesson on this, by the way, guys, because I need to do all of them. But you learned loads of chemical tests at GCSE. One of them was the test for the halide ions, silver nitrate. So if I've got sodium chloride, aqueous, salt water, and I want to test for the chloride ion, what I'm going to add to it is silver nitrate solution. Now that. And what's going to happen is I'm going to form silver chloride, which is a white solid, and sodium nitrate, which is aqueous, because all aqueous, all nitrates are soluble. So it's always aqueous. Right, we can now convert this into an ionic equation. So all the aqueuses are going to become their ions. Na plus Cl minus plus Ag plus NO3 minus goes to, it's a solid, I'm not going to separate them, plus aqueous, Na plus and NO3 minus. And what you realize is the Na pluses haven't changed. The Cl's have, but the nitrates haven't changed. The final equation, Cl minus plus Ag plus goes to AgCl, a white precipitate. So ionic equations are used when you're trying to show them actually who is actually doing stuff. And we relate it to chemical tests because if you do a chemical test and something appears, it's like, oh, I've made something special. What's causing it? And usually it's because you're forming an ionic solid, which won't be soluble. So it then is going to need its ionic equation showing what ions are doing what. So the red ones are spectators. And the other ions are the species doing the work. So in terms of my learning objectives, and I've only got 2 minutes left, so I've got to end the lesson here. Ionic equations and when to use them. When they ask. That's it. When they ask. Write ionic equations. We can start doing that now. And the chemical tests one I will do in another lesson. I'll do all the chemical tests because it's going to be a long lesson. That's going to be a little bit of a sequence, to be fair, about 3 lessons to cover all of them. But guys, this brings us to the end of Ionic. We are done. I'll give you the worksheet on ionic equations, and you can have a practice of doing them. Yeah, they get quicker over time as you start to understand what they're doing, but I'll give you a homework on those too. Right, guys, I'm going to end my lesson there, bring it to a close. Guys, I hope you all have a wonderful weekend. Stay safe, do something nice, enjoy yourselves. And your ionic assessed homework is on Tuesday. It's not like that. Your next lesson. I'll see you guys later.